quotient, 0 over 0 or infinity over infinity. Okay, so let's kind of recap. We've seen a few indeterminate forms now. So the first day we started with the basics. 0 over 0, infinity over infinity. If you have either of those, what do we do? Do our L'Hopital's to simplify it. And remember, L'Hopital's rule just says derivative of the top divided by derivative of the bottom. It's not the true quotient rule. And so please make sure that you are using good notation. That means you should be writing the limit up until you take the limit. When we do L'Hopital's, I've asked you to kind of notate that, write the LH over the equal sign so we understand what we're doing. So if it's 0 over 0 or infinity over infinity, we can do L'Hopital's. But yesterday you realized those are not the only indeterminate forms. Indeterminate forms are basically anything that we look at and we can't decide what that limit's going to approach. So if you have 0 times infinity, okay, we know 0 times anything is 0, but infinity times a number is infinity. And so it depends on the problem, whether depending on how fast you're approaching infinity or 0. It's not a clear-cut answer. So this is an indeterminate product. But we can't just go straight into L'Hopital's because L'Hopital's only works for 0 over 0 or infinity over infinity. So the strategy on those needs to be to write it as a fraction. Then L'Hopital's. Now we're not just like making up a fraction. It has to be something that works. If you have the limit as x approaches 0 of like x cubed sine of 3x. Okay, can you just say, oh sure, I have to write it as a fraction. That's the same as sine over x cubed. Are those mathematically the same? No, so you're not just like throwing one thing on the bottom. To make it into a quotient, you have to divide by the reciprocal. Okay, what's the reciprocal of x cubed? 1 over x cubed. So if you want to make it mathematically the same, you would have to make it a 1 over x cubed on the denominator. So you can't just throw anything down there. Easy things to look for: if you have x's to a power, you can easily move those to the bottom by doing 1 over that thing. Sine and cosine, we don't necessarily want to move, but if you have like a cosecant, secant, those will be nice to move because if you put those on the bottom, what is the reciprocal of cosecant? Cosecant is 1 over sine, so the reciprocal would be sine, so it would just be putting a sine on the bottom. If you have a cotangent, when you move that to the bottom, it would become a tangent. So if you have one of those reciprocal functions, those are nice to move to the bottom because it would become the sine, cosine, or tangent. If you have something with a negative power in the beginning, so if I have like e to the negative x times something, I'm not necessarily making up problems that work, just so you know. I'm just kind of making up something right now. You have to move one of those to the bottom, but what's a nice one to move? Yeah, because if you do the reciprocal, well, the reciprocal of a negative, doesn't that negative just mean it's on the bottom? So you look for the easy things to move. X to a power, you can make it 1 over x. If you already have something with a negative exponent in the problem, negative exponent means it goes to the bottom. If you have a cotangent, what would that put on the bottom? Tangent. Does that mean you can't move the other one? No, but this would be easier. So you're kind of looking for the easier thing to move to the bottom. And then once you do that, you have to verify, is it 0 over 0 or infinity over infinity? And if it is, then you can do L'Hopital's. Then we have next indeterminate form, infinity minus infinity. Okay, we want to just say that's 0, but there's actually degrees of infinity. Infinity can be a lot of different things. We just means it's getting bigger. So if one's increasing faster than the other, then it's not just necessarily going to turn into 0. And so a lot of these problems were already fractions. If you have a fraction minus a fraction, what do you have to put those together? Common denominator, so that we have a single fraction. And then, once you have a fraction, you check to see if you have 0 over 0 or infinity over infinity, and if you do, you can do L'Hopital's. All right, so those are the 3 we have seen previously. Your homework had 3 of the product ones and 3 of the difference ones, where you had to be looking for a common denominator. Today, we are going to look at the final types, and then because I was gone yesterday, I'm going to give you guys a little extra time, so if you have questions, you can get them answered. So we are going to turn in all of this section's homework on Monday, but that better mean it's done Monday. So if you need help, you better be coming to see me, okay? So, indeterminate powers. Let's look at our book. This gives a very nice kind of layout. Page 306. All right, so it tells us kind of in the middle of the page, several indeterminate forms arise when you have the limit as x approaches a of a function to a function. Okay, so 3 different issues we might see. We can see something of the form 0 to the 0 power. Okay, we know 0 to any power is, like, what's 0 to the second, 0 to the third, 0 to the fourth? 0, but any number to the 0 power is 1. So it's not obvious what this would go to. We kind of have conflicting rules. So this is an indeterminate form. We don't know what that means. The second one, infinity to the 0. Okay, we know infinity to any power, to a positive power, is going to infinity. But something to the 0 power is going to 1. So this is kind of contradictory again. We don't know what that's going to turn into. The final one is 1 to the infinity. Because 1 to any power is 1, but a number to the infinity is going to infinity. So these are the final 3 indeterminate forms, things that we cannot just look at and know. And it will depend on the problem, basically, which function is increasing faster, what's going to win out. So the strategy, it says each of these 3 cases can be treated by taking the natural logarithm or by writing as an exponential. Okay, so this is a little more complicated. The reason we would add a natural log to this is if we think back to properties of logs. If I have the natural log of a to the x power, properties of logs, what happens to the exponent? It goes to the front. And now this is a product, and yesterday we saw products. What do we have to do? Turn them into quotients, right? So we can turn it into a quotient. And then once you get to that point, you can do L'Hopital's. Now, you can't just throw natural logs into a problem without changing it, right? What's the opposite or the inverse of a natural log? E, the exponential. So what we'll do is basically do the natural log at the beginning, work it all out, but then our answer, we're going to have to throw an E in. So if we had taken this problem, if I make e to that power, the e in the natural log cancel. So when we have these indeterminate powers, it's a 2-step process. First, we'll do the natural log and do all that, and then our final answer will be e to whatever power we get. So let's look at one. I want the limit as x approaches 0 from the right of 1 sine of 4x to the cotangent x. The very first thing, you can't just assume that something's indeterminate. We need to look at it and actually decide. So if I put in a 0, what is the sine of 0? 0. 1 plus 0 is 1. Okay, cotangent of 0. So we know tangent is top over bottom. So cotangent would be bottom over top. So it's got a vertical asymptote there, so it's infinity. So 1 to the infinity, is that an indeterminate form? Yes. So our strategy, we want to get rid of this exponential. The only way to get rid of that exponential is to add a log, because properties of logs, the exponent can come down. So what we're going to do, we keep our limit and we are writing it on every step. We're not just trying to save paper and squeeze something in. We're going to add a natural log. And because I added a natural log, I know that my final answer, what do I have to add in? E. So my final answer will be e to whatever power I get out, because an e and a natural log cancel one another. So now properties of my logs. The exponent can come down. Okay, and then this is a product like we saw yesterday. And when we have products, what do we want to do with those? We need them to be fractions. Which would be easier to move to the bottom, a cotangent or a natural log? Cotangent. Don't ever try to move the natural log to the bottom. It will create all kinds of headaches for you. So we're going to leave the natural log on top. But to move it to the bottom, you have to put the reciprocal on the bottom. What's the reciprocal of cotangent? So now, we can't just assume L'Hopital's, we have to check. If I put in a 0, here he said sine of 0 is 0, 1 plus 0 is 1. What is the natural log of 1? 0. It's like saying e to what power equals 1. Over, what is the tangent of 0? 0. So this is now 0 over 0, which is the indeterminate form we want, because now we can do L'Hopital's. Our limit stays, and you guys have good notation, so you are writing that. Now, how do we do the derivative of a natural log? 1 over the argument. Divided by, oh, I'm not done. 1 over the argument, but then what do we have to do? Chain rule, derivative of the inside. So derivative of sine is cosine. The inside stays the same. And then times derivative of the 4x is 4. Over derivative of tangent. So if you have forgotten some of your derivative rules, this will be a great time to refresh them. You need to know the derivatives of your logs, derivatives of your trig functions, and remember our chain rule. Are there any questions on how I got here? Now this looks like a horrible mess, and it might be, but let's see if we can evaluate it yet. If I put in a 0, the sine of 0 is, so I have 1 over 1, which is 1, so that's okay so far. 4 times 0 is 0. Cosine of 0 is 1 times a 4, so the top is good. Over secant of 0. Secant's the reciprocal of cosine. Cosine of 0 is 1, so the reciprocal of 1 is still 1. So it was a mess, but we got an answer. The answer is 4. But we made a note to ourselves, 4 is not really the answer. Because we added a log, we have to cancel it, so we add an e. So our final answer is e to the 4th power. All right, it's really testing our brains there. Lots of thinking back to it, evaluating our trig functions, derivative rules. What questions do you guys have? So currently, if I plug in a 0, what am I going to get? 0 to the 0. Can we evaluate that? No. What's our strategy? Right, we need that exponent to come down, so the only way to do that is with a log. If 1 is x approaches 0, of the natural log of x to the x. And I'm going to make myself a note. I added a log so I can't forget my e. The reason we do the log is that the exponent will come down. But now it's a product. Is that going to help me? No. So we have to rewrite it as a quotient. Which one are we going to move to the bottom? X. And we are moving the reciprocal because mathematically it has to be the same. So multiplying would be the same as dividing by the reciprocal. So that would be a 1 over x. Or you could write it as x to the negative 1 if you prefer. Have I lost anybody? What is the natural log of 0? Does that even exist at 0? No, but if you think about logs, remember this one is approaching, we have an asymptote there. So we know it's going to negative infinity. 1 over 0, 1 over a smaller and smaller number is going to infinity. So this is infinity over infinity. So now we can do L'Hopital's. What is the derivative of the natural log? The argument, my argument is just x, so we don't have to do the chain rule. Okay, the denominator, that was x, 1 over x. You can think of that as x to the negative 1. So what's the derivative of x to the negative 1? So that's like a negative 1 over x squared. Can we clean that up at all? Yeah, if we're dividing two fractions, that's the same as multiplying by the reciprocal. So that's like 1 over x times negative x squared over 1. Which just turns into oh, hold on. I turned my 0 into an infinity on my limit, didn't I? Okay. Good. I was just looking at that thinking, we're not going to get a nice answer. Okay. So now can we plug in our 0? And we get 0. So my final answer is not 0. It is e to the 0, and anything to the 0 power is 1. So this limit is going to 1. All right. I know I did some of these examples in yesterday's video. What example are we ready for? 12. So that's good. That gives me one like yesterday. So if I plug this in, I get the square root of infinity squared plus infinity, so that's just infinity, minus infinity. Can we work with that? No. Is this the problem we would add a log to? No, because it's not an exponent. Okay, so I told you that our strategy is to try to write these as a fraction. Now, most of the examples you saw yesterday were already fractions. I think they both were. So we could just get a common denominator. This one is not, but think about other things we've done with radicals. This is like over 1. What's something we commonly do when we have problems with radicals? Yeah, let's multiply by the conjugate. The conjugate would be the square root of x squared plus 3x plus x. And we have to do it on top and bottom. So on the top, x squared plus the square root of x squared plus 3x times the square root of x squared plus 3x. Just cancel the radical. Because they're conjugates, outside and inside cancel. Minus negative x times x is negative x squared. So on the top, my x squareds cancel. And we get to here. All we've done to this point, this isn't calculus, this is just algebra. We were reducing things. If I look at this, 3 times infinity is infinity. On the bottom I have infinity plus infinity, which is infinity. So infinity over infinity tells me what? L'Hopital's. Right, derivative of 3x is 3. On the bottom, a square root, like we said before, is a 1/2 power. So derivative of the outside, so the 1/2 comes down, inside stays the same, subtract 1 from the power, but we have to do chain rule, so times derivative of the inside would be plus derivative of x is 1. All right, this is pretty gross. On the bottom, this negative, we'll put it on the denominator. So it'll be like a 2x plus 3 over 2 square root of x squared plus 3x. That's a 1. Can I plug infinity in right now and know what it's going to turn into? Not really, because this fraction right here would be infinity over infinity, which means we don't know. I don't really want to try L'Hopital's from here. This is pretty awful. So let's keep trying to clean it up. The thing that makes it so ugly is the fraction in a fraction. So to simplify that, let's multiply everything by that denominator. So on the top we would get 6 times the square root of x squared plus 3x. On the bottom, those cancel in this term, so that's a 2x plus 3, plus 1 times that. Okay. If you plug in infinity right now, what are you getting? Infinity over infinity. So what does that mean? L'Hopital's, but that's going to get really bad, isn't it? Don't forget the other strategies. We had problems infinity over infinity before. We had them on every single horizontal asymptote we were finding on the previous sections. What did we do on all of those? 1 over the highest power of x. Okay, so my highest power of x is an x squared, but it's under a square root. So we're going to multiply by 1 over the square root of x squared, or that's the same as 1 over x, right? So basically, anything with the square root, we're doing the x squared. Anything without a square root is just 1 over x, because mathematically those are the same. So we have a 6 square root. So since This is under a radical. We're going to multiply by the 1 over x squared under my radical. So x squared over x squared would be 1 plus 3 over x. On the bottom, 2x plus 3 is not under a radical. So we're taking it times 1 over x. This is under the radical, so it's the square root of 1 over x squared. And this is actually pretty helpful, because if we have a number over infinity, what does that go to? So at the top we have 6 times the square root of 1, which is 6. On the bottom we get 2 plus 2, which is 4. So overall 3 halves. That was a pretty ugly version of one of the indeterminate differences. Questions on that one? I think I'm going to do one more, and I'm going to give you guys some time to work. Cosine of 0 is 1. 1 over 0 is going to infinity. 1 over infinity, can we do, or 1 to the infinity power, can we do that? No. So what do we do? Add a log. And I know because I added a log, my final answer will be e to some power. So property of logs, exponent comes down. And this one's pretty easy to write as a fraction. What would it be? Just x squared, because it was already, if you multiply those, 1 over x squared times natural log, it creates a fraction. Okay. Cosine of 0 is 1, natural log of 1 is 0 over 0 squared. So now it's 0 over 0, so now we do L'Hopital. Okay, natural log of cosine. So the derivative of natural log is 1 over the argument times derivative of the inside. What is the derivative of sine? Or sorry, cosine? Negative sine. Okay, on the bottom, derivative of x squared. 2x. Different approaches from here. On the top I have negative sine over cosine. What is sine over cosine? What is tangent of 0? 2 times 0 is 0. So what does that mean? L'Hopital's again. So limit of x approaches 0. Okay, what is, we have a negative, what's the derivative of tangent? Over derivative of 2x is 2. So we have a negative. Secant is the reciprocal of cosine. Cosine of 1 is, cosine of 0 is 1. 1 squared is still 1. So we get negative 1/2. So our final answer is e to the negative 1/2 power. All right, so you have problems already from when I was here and what is today? So when I was here Wednesday and from yesterday, you had 6 new ones. Today, I'm adding 4 more. All of these are due Monday, and then Monday we are going to take another day and practice all of this before we move on. So we're not ready yet, especially with me being gone for a day. I'm not going to move on quite yet.
Do you have a bigger so that I can come in